Hi there! Today the subject of our video is the rectifiers. We will take a look at them, discover what they are and how do they work. Let's get into it. To begin with, we have to do some classification in terms of rectifiers. There are two main kinds of rectifiers. Those defined as half wave, and we will see later on what that means, and those identified with the name full wave rectifiers. For the full wave rectifiers, we have two different kinds actually. One is what is called the center tapped transformer rectifier, and the other kind is what is called the bridge rectifier. Many people sometimes address the bridge rectifiers, the full wave bridge rectifiers, as simply full bridge rectifiers, but really the correct name is full wave bridge rectifier, or full wave center tapped transformer rectifiers. Let's see what they are. Before talking about rectifiers, we need to introduce one electronic component which is named diode, and which is the main component of rectifiers, either half wave or full wave. A diode is basically a component that provides flow of electricity in only one direction and not the other. So this is the symbol of a diode. And if we connect to a circuit where the voltage is with the positive on this side, which we call anode, and the negative on this side, which we call the cathode, then current will flow to the diode in this direction. Conversely, if we set the voltage on the opposite way, so with negative on the anode and the positive on the cathode, there will be no current flowing through the diode. The current would want to go in this direction, but really the diode does not allow for that. So the diode basically is a device, an electronic device, that allows the flow of the current in one direction only and prevents the current from moving into the opposite direction. To see how a rectifier works, we have to draw a simple electronic circuit. This is its schematic. We have this device over here, which is called transformer, which I represent this way. And this device basically is capable of taking the 110 or 120 volt AC that comes from a plug in the house to a different voltage on the other side, which can be either lower or higher than the voltage at the entrance. What we do usually for powering electronic devices, if we have a transformer that works in such a way that the voltage goes down from what is called the primary to the secondary. So it is a down transformer. So if we measure the voltage at the secondary, we find a voltage that is lower than the voltage at the input of the transformer. So let's assume, for example, that we have a 12 volt AC over here, but any other voltage would work as well. And now let's connect to one side of this transformer, for example to the upper wire of it, a diode in this position. And then let's connect a load to this circuit, or resistance RL. In this condition, we have what is called a half wave rectifier. It works this way. So first of all, let's represent the voltage over here at the output of the transformer. So voltage of the transformer in terms of time is basically a sinusoidal wave that we can represent this way, and so forth. So what happened when this wave is applied to the diode? So this is basically the voltage over here. Let's call it VI. And then now let's talk about the voltage at the output. On this side, VO. So let's take some important points here. So we have to consider this point in time over here, this point in time over here, this point in time over here. Now the signal, the voltage on this side of the diode, on the load RL, will look like this. So why is that? Basically, during this part of the cycle, the diode will be polarized with the plus on this side and the minus on this side. So it will allow the current to flow. So current will flow through the load and will generate a voltage VO on it. So this is the voltage, which is proportional to the input voltage over here. But when we go to the second part of the wave, when basically the voltage over here flips around, then we will have a negative voltage applied over here and a plus voltage applied over here. At this point, the diode will oppose to the flow of the current and will not make it flow. Since there is no current into the load RL, there will be no output voltage, and so in this interval, there will be no voltage over here. Then the voltage will flip again, it will become again plus on this side and minus on this. We will have again a voltage over here. So as you can see, of the whole wave that comes over here, only half of it is reproduced on the output. The other half is lost. And that's why we call this rectifier a half-wave rectifier. Why it is a rectifier? Because this is an alternate current. But this is not, because it can be only positive. There is no negative over here with respect to ground. So this is basically DC current, although not constant, it's gonna pulse this way, but still it's DC current, because it always will be positive on this side and negative on this side, never the other way around. Let's draw again the schematic for a half-wave rectifier. We have the transformer over here. Input side and now output side. Then we have the diode. And then we have the load. As we have seen, the voltage on the load has a shape like this. That repeats indefinitely. But this is not really the way we want to power electronic circuits. We want a voltage that is mostly constant over time. So how do we do that? One way of doing this is to add a capacitor over here. Usually we use an electrolytic capacitor, which therefore is polarized. This is this plus side because the voltage will be positive on this side. What happened when we add the capacitor in this kind of circuit? Well, let's draw it over here. During the first half wave, the capacitor will start to charge from this point to this one, and will follow, and the diagram of the voltage on the RL load will be exactly like that. However, when the voltage starts decreasing, the capacitor is charged and would like to maintain the voltage always at the same level. However, part of the charge will be discharging on the load, and so there will be a current that goes here, while this is negative, and this is positive. So there will be no current in here, but there will be a current from the capacitor to the load. So the capacitor will start discharging. It will discharge until it reaches this point. Then, at this point, there will be again the positive on this side and the negative on this side, and so the capacitor will start charging again this way, and then it will start discharging again, and so forth. So as you can see, now we are going to have a voltage that never goes to zero, but keeps a value higher than that. And there will be an average of it, which is around here. And this is the actual voltage that a multimeter applied over here would reveal. However, if we put an oscilloscope over here rather than a voltmeter, we will see actually this kind of wave that never goes to zero, that has an average that is basically like this, but also is a voltage that increases above the average for a certain amount of times, and then goes below for other amount of times. The higher is this current that goes from the capacitor to the load, the faster the capacitor will discharge, and so the faster will decrease the voltage. So when the load increases, this discharging curve will be more pronounced. Up to the point that if the load requires a lot of current, the capacitor may end up being completely discharged before it starts charging again. So putting a capacitor over here helps in preventing that the voltage at the connectors of the load goes entirely to zero during the negative waves of the alternate current. But still, as you can see, it can really go to zero if the current is high enough. This is a limitation of the half-wave rectifiers, which have a pronounced variability of the voltage, even though it's still a DC voltage. Let's now take a look at full-wave rectifiers. As we said already, there are two kinds of full-wave rectifiers. There are the center-tapped transformer rectifiers and the bridge rectifiers. Let's take a look at each one of them. Let's start with the center-tapped transformer rectifier. So when we draw the transformer in this kind of circuit, we have a slight variation at the output of it. There is an extra wire that is connected exactly to the center of the wires of the transformer. So basically we have three wires, and it works this way. Let's represent the output, the voltage over here, with respect to the input. So on the input side over here we have a voltage which is like this. And this is the same kind of shape that we can have from here to here. So between these 2 points we are going to have a certain voltage. Between these 2 points we are going to have a different kind of voltage, let's call it V1. And between here and here we are going to have another voltage which we call V2. The V over here, VO, is the sum of V1 plus V2. When this terminal is positive, this one will be negative. When this is negative, this one will be positive. We can consider the center tapped of the transformer as the ground wire for the circuit that is going to be powered by this transformer. So basically this plus and minus, minus and plus, can be considered with respect to this point. Of course, with respect to this point, V1, with respect to the ground, will be half of VO, and the same for V2, will be half of VO. So when we want to represent V1 and V2, we basically have a similar diagram, but if this is VO, V1 will be something like this, and V2, similarly, will be something like this, a lower value which is half the amount of VO. Now, let's see how we can use this kind of transformer to generate a DC voltage. So we have the transformer over here with its 3 wires. Now what we are going to do, we are going to put a diode over here, exactly like a half-wave rectifier we already seen, and another diode over here, same thing. Then we are going to connect these 2 points, and then we use this one as the output. So basically this one is the new voltage output, and here we can connect our load. How this works? Well, it's relatively simple, though a little bit more complicated than the previous case, but you will see there is a big difference from the previous case. So, let's make 3 diagrams over here, all against T. So this is the V1 we saw before, which is here, considering it over here. The V2, we are going to put it over here. And then this is considering the VO now. So everything would be measured now against this point, which we said we consider it as ground. So when on the transformer this side is positive and this side is negative, we will have this diode that basically let current go through because the anode is positive, and this current will go through the circuit this way, through the load, and then back to the transformer. This diode here will not work, will be basically working as an open switch, because the negative is applied to the anode, and we know that in this case it prevents the current from flowing. So during the positive side of the wave over here, this diode will conduct electricity, current, and we are going to have a voltage over here which basically follows this same curve. So this is V1 here, and the output over here is exactly the same. Now, when we go to the other half of the wave, this side becomes negative and this side becomes positive. Now, of course, in the previous case when this was positive and this was negative, V2 was not there because this side is not conducting any electricity, so there is no voltage over here. Now, with the minus over here and the plus over here, this diode works as an open switch, while this one works as a closed switch. So we will have current over here and we will have none over here. So V1 goes to 0. V2 instead will act like this wave, but so it will work this way. However, this V2 goes up over here to the same side of the load where we had voltage with this diode. So on VO, actually, we are going to have something like this. Look at that. Instead of having half wave on the output on the load, we are going to have 2 half waves. So we are reusing the whole wave, the full wave on the input, on the output, by basically flipping on the other side the voltage, the negative voltage is over V2, just because the connection is done this way on the load. So this is the way a full wave rectifier works. So now we have 2 waves, now we have 2 half of the waves that are both reused on the load, generating a voltage that is still DC, like it was with a half wave rectifier, but that has an average voltage higher than the previous one, than the one that we saw in the half-wave rectifier, just because there are no periods of times where there is no voltage at all. Now, like we saw in the half-wave rectifier, we can add again a capacitor over here. This time, the capacitor again will start charging in this interval, then will start discharging over here, but as soon as it reaches this point, it will start charging again. And then it will start discharging again. Let me do it with another color. Apparently the red doesn't work anymore. So this is the way the capacitor works now. You see, it's going to be similar to the one we saw with the case of the half-wave rectifier, but this time the capacitor has less time to discharge. In the previous case, it would have discharged until this point. Now, only until this point. So, if we set up appropriately the value of the capacitor, depending on the kind of load that we have, we can make sure that the voltage here never goes to zero and actually maintains higher values with respect to the half-wave rectifier. Let's talk now about the full-wave bridge rectifier. This time the transformer is a normal one, with only 2 wires on the output. But we apply on this output 4 diodes that act as a rectification, a full-wave rectification, that are connected this way. And then this will be connected this way. And this way. Now we take this, we go over here, we take this, and we go over here, and we apply here the load. Let's see what's going on. Let me use a different color to do that. So this is the wave over here. Let's call it the VI. VI is a full sinusoidal waveform. So when we are on the positive half wave, there will be positive over here and negative over here. This diode, because of the positive over here, and since this is the cathode, will be off, so there will be no current flowing over here. This diode, since there is positive on the anode, will be on, so there will be current flowing over here, and the current will flow like this, through the load, and going back over here, since this is off, the current will go over here, which is on since there is a negative on the cathode, so the current will go over here, so basically through here, up here, then through here, and back to the transformer. So we have a voltage in the output, VO, which I'm gonna draw over here, which resembles the same half wave with a positive on top. Now, let's go to the other half wave. Oh, I still needed this one. So with the other half wave, we will have the negative on this side and the positive on this side. Now with the negative on this side, this is going to be on because the negative is on the cathode. This is going to be off, so current can flow over here in this direction. On this side, this diode will be on because the plus is on the anode, so the current can flow on this side. And this other diode will be off because on the cathode there is a plus sign. So with the plus over here, we can have a current flowing through here, go through the diode, and then go through here, inside there are the load in the same direction as the previous one, and then back over here, back to this diode and to the transformer. So, on the load, we have another voltage of sinusoidal shape, which has positive on this side as negative on this, exactly like this case here. So, it's going to be something like this. Look at that. We have basically flipped around the second half of the wave, and we have obtained a full wave rectification, even without the tapping at the center of the transformer. However, we had to use 4 diodes instead of 2. That's a big difference. So again, this is another way of obtaining DC voltage from an alternate voltage. Again, here we can add a capacitor, same way we did with the previous full wave rectifier, and that again will produce a wave that goes this way. The capacitor discharges till this point, then charge again, and keeps going this way. So again, we are going to have a voltage, DC voltage on the output, on the load, that is much better sustained than what we had with the half-wave rectifier. And that's just because the interval where the capacitor discharges is smaller than the one of the case of the half-wave rectifier. You see, in the half-wave rectifier, the capacitor discharges from here to here, because there is no voltage on this side. I'll show you from here to here, because there is no voltage on this side. And only when the voltage comes up again, then it will start charging again. With the full wave rectifier, the capacitor will discharge here up to this point, much shorter amount of time. So the capacitor will be able to hold much more charge during this interval and will not go to zero entirely, as it could have happened with half-wave rectifier. This works much better, and this is why in electronic circuits we prefer to use full-wave rectifiers rather than half-wave rectifiers. Now, why would we choose a center-tapped transformer rectifier versus a bridge rectifier when we need a full-wave rectifier? Well, let's draw some comparisons and let's understand why we prefer one to the other, depending on the situation, basically. Because both of them have both pros and cons. So let's take a look at those. So let's draw the two kind of full wave rectifiers that we know about. The first one, which is the center tapped transformer rectifier. And the full wave bridge rectifier. You see, if you want to draw a full bridge rectifier, there is an easy way to do that. On one side, we draw a diode in one direction, like this for example, and on the same side, the other diode will be in the opposite direction. Down here, we will do the same thing, but this will go like this one, and this will go like the other one. And then in this case, since the diodes are set this way, we are going to have the negative on this side and the positive on this side. And here is our load. So plus and minus, plus and minus. Now, let's compare these two circuits. First of all, if we need a voltage, let's say 12 volts over here, for both cases, in this case, we need a transformer that gives us about this average voltage, 12. But in this case, since we take only half of the voltage in each half wave, we will need a transformer that provides an output voltage that is double the amount of this one. So if the output over here is VAC, the output over here, between this point and this, has to be 2 times VAC. So from this perspective, this circuit is a disadvantage with respect to this one, because we need a transformer which has a higher output voltage, and in addition to that, has to have a connection to the center of the filament on the secondary side. But now let's look at the diodes. For every half wave, either this diode will conduct electricity, will conduct a current, or this one, never both together. So either the current goes through diode D1 for the half wave where here is positive and here is negative, or when the half wave is negative on this side and plus on this side, the current will go to the diode D2. In this case, instead, whenever the positive is here, the negative is here, or the negative is here and the positive is here, we will always have 2 diodes that conduct electricity. For example, plus over here and minus over here. Then the current will go through this diode, through this circuit over here, then through this diode, and then out over here. And vice versa, when this is negative and this is positive, the current will go through here, then here, 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 and back here. So, in every half a wave, we have to go through 2 diodes in this circuit, and only through 1 diode in this circuit. So although we have different kind of transformers and this costs a little more, with these circuits we have to use only 2 diodes, while in this we have to use 4. So this is already a saving, especially if we have to work with very high currents. Diodes are going to impact much on the cost, because diodes that work at a high current cost more, much more, than diodes that work at low current. So from the diode's perspective, this would be a more economic solution than this one. But there is one more thing to keep into account. When current flows across a diode, it's not that the diode acts exactly like a closed circuit, like a switch that is closed this way. But there is also a slight resistance within the diode that we have to keep into account. So the diodes, when it's closed, behaves more like this, like a closed switch plus an internal resistor, which has, when the current flows through it, a little voltage drop across this resistor, which we call delta V. And for usual rectifier diodes, which are made of silicon, this delta V is around 0.7 volts. So with this circuit, since we go only through one diode every time the phase flips around, the half wave positive and the half wave negative flip, so there will be always a voltage over here, which is 0.7 volts lower than the one at the output of the transformer, because of the drop in voltage across D1 or across D2. But with this circuit, since we have to go through 2 diodes at the same time, there will be double the amount of drop because of 2 diodes. So the drop will be 1.4 volts, which is twice the 0.7 of before. And so the voltage over here on the load will be 1.4 volts lower than the one on this side. So this is kind of a disadvantage of the full bridge rectifier, because for lower voltages it becomes less functional, because we are going to drop double the amount of voltage than in this case. There will be more loss of energy due to heat dissipated on the diodes because of the higher voltage. So this becomes less convenient because of the higher drop in voltage. So when to choose one and when to choose the other. Let's say we need a circuit, a rectifier, that has to work with high voltages and low currents. In that case, we prefer this solution, because with higher voltages, the drop of 1.4 volts will be negligible with respect to the full voltage over here. And this one instead becomes more convenient for high currents and low voltages, because with high currents we will need diodes that are more expensive, and using only 2 instead of 4 of them, it will be more convenient from that perspective. Now, this is kind of a fine line. Really, there are cases where the voltage and the current are such that there is really no gain in terms of cost of the circuit in one case or the other. So the choice becomes just a pure preference from the perspective of the designer. And this is actually the case where most of the normal electronic circuits work. There will be mostly a voltage and a current that are in that range where either one of two is most effective in terms of costs. However, if you have circuits, cases where you need really a high current, this has to be the preferred solution. And when we have cases where we have a really low current but a higher voltage, this becomes the preferred solution. When I talk about higher voltage, they become convenient only when the voltage goes higher than 20-30 volts. For anything below that, this works better because there is less drop across the diodes. So let's go back now to the half-wave rectifier. So we have a transformer, we have a diode over here, a load, and I'm gonna put now a probe over here from an oscilloscope and another probe over here, so we can measure the voltage over here and the voltage over here and compare them and see how they look like. So here is the circuit. We have the transformer over here. There is the diode over here and the resistor that acts as a load or connected over here. All according to the circuit I just drew. This one. So let's see how this looks like on the oscilloscope. So now let's take a look at what the oscilloscope shows us in terms of the signal coming out of the transformer and the signal after the rectifier on the load itself. This probe is the blue one. It goes to the channel 2 and is shown here on the monitor like a blue wave. You can see this is a perfect sine wave. Let me show you this way so you can better see it. And so it has all the both halves of the signal, the positive half of the wave and the negative half of the wave. On the other end, on this other probe, the yellow one, it goes to channel 1, which is the one that is shown here in yellow also. And you can see that there are only the positive half wave represented here. Let me shift it a little bit so you can see it better. So you see, when there is the positive half wave of the input signal to the rectifier provides as an output that same shape of the wave. Whereas when there is the negative half wave on the input of the rectifier, the output is just zeroed. There is nothing over there. The other thing you can notice is that the yellow signal is just slightly lower than the blue one, and this is because of the voltage drop on the diode. And these are the 0.7 volts I was talking about before when working on the diagrams. Let's take a look now at what happens if I add to the circuit a capacitor in parallel to the load. So let me put this over here and this over here. Okay, as you can see now, the signal on the output is totally changed, because now there is the capacitor that is able to charge during the beginning of the positive half wave, and then discharge during the whole negative half wave. So you see the capacitor is charging over here, and then when the wave goes below the value of the capacitor, the voltage value of the capacitor starts discharging and keeps discharging until it intersects again the coming up of the wave of the input, which is basically the one from the transformer. So here it starts charging again, and then it discharges and charges again and discharges and keeps going this way. So basically the capacitor is capable of providing current in terms of electric charges through the load when the signal is on the negative part of the sine wave. Let's take a look now at the full wave rectifier, and in particular the full wave bridge rectifier. I'm not going to talk about the other rectifier, since it works basically the same from the perspective of these diagrams, so I will show you only one. Let's do that. So let's take a look now at the full wave bridge rectifier. Again, we have a transformer over here. This time we have 4 diodes set over here, such that this diode will be with the positive over here, and this diode will be with the positive, or better, the anode over here. And these are the 2 diodes the other way around, the cathode over here and the cathode over here. So each end of the transformer will be connected to 2 different diodes at the same time, one on the cathode side and the other one on the anode side, and the same on the other side. The 2 cathodes of these 2 diodes go together, the 2 anodes of these diodes go together. So these made up the positive side of the DC voltage on the load, and these 2 will make up the negative side of the voltage on the load. The probes will be attached again on the load and on the transformer. Unfortunately though, this time I cannot attach the 2 probes at the same time. I would have to attach one and leave the other disconnected, and then I have to disconnect this and attach this one. And the reason for that, as you see, is that since this is the ground of this probe and this is the ground of this other probe, I will basically connect this line and this line at the same time to ground. So I will short this diode, and I will put this other diode directly in between the 2 ends of the transformer, taking the chances to burn it, basically. So I cannot do that. And this is because the 2 entry points, the 2 inputs of the oscilloscope, both have the 2 grounds connected together. So I cannot do this. So one at a time. So let's see how it works here. So now I have the 2 ends of the transformer, which are connected, one on these 2 diodes, the other one to these other 2 diodes, and then the other end of the diodes is connected to the load. And right now I have disconnected this probe and connected only this other one, which is connected between the 2 ends of the transformer. So let me power up the circuit. There we go. And here is the signal, which is a sine wave, of course, because this is an alternate current coming from the transformer. Let me disconnect the probe from here now, and let me connect to the other side this time. So one goes over here, and the other one goes over here, so we'll be in parallel to the load. And take a look now at the oscilloscope. Now we can clearly see that this is a full wave rectification. Now the positive half waves from the transformer goes directly over here. 1, 3, 5, 7, and so forth. Let me do this, it's easier to see. So positive and positive, and the negative side of the wave is flipped over and put over here. So now we have, for each full sine wave of the input, we have 2 half positive waves on the output of the rectifier. Now let me add the capacitor, like we did before. I can connect it on the 2 ends of the load. Okay, now that the capacitor is in place, you can see that the wave here is like the one with the half wave rectifier, but you can see that the ripple here, so the difference between the highest voltage and the lower voltage, is much smaller than the one we had in the previous case. This is another positive thing of the full bridge rectifier. The ripple of the signal is much less, so the signal coming out of the full wave bridge rectifier resembles more closely the one of a DC current of a constant value. Today we explored the rectification circuits which transform AC current to DC current with the help of one or more diodes. We have seen that there are 2 main types of rectifiers: the half-wave rectifiers and the full-wave rectifiers. And we have also seen that there are two kinds of full-wave rectifiers, the center-tapped transformer rectifiers and the bridge rectifiers. We have finally seen how these rectifiers work, and we have made a couple of experiments to verify the validity of the theory. In the future, I will propose other tutorials that will expand on the subject of rectifiers, introducing voltage regulators and current regulators and limitators. At the end of this series of tutorials, I will put all together by showing you how to build a workbench linear power supply, very useful especially when working on audio projects. Please don't forget to subscribe to this channel if you haven't done so already, so you will not miss any of these future videos. See you on the next video, and as usual, happy experiments!